Okay, we are talking about dark matter, the evidence for dark matter. And I promised you last time that I will show you a few pictures today. Actually, we have a kind of technical problem because the room is not optimal for this plan. We cannot get it really dark, but I hope you can you get the general idea what is shown in the picture. We were talking about the rotation curves of galaxies, and here's an example of such a rotation curve. They look more or less the same for a very large variety of galaxies. So I told you last time what you expect. So what is plotted here is a radius, the distance from the center of the galaxy, and the orbital velocity which you observe via redshift. Yeah? So you look at the galaxy edge on. You see on one side it's moving away from us, on the other it's coming towards us. And the velocity makes itself felt by way of a redshift. That's what measured here. So I told you that Vera Rubin did this kind of observations over many, many years. And here's an example for one galaxy. So what you expect is from the mass which you actually see. You see the mass, a large portion of the mass concentrated near the center of the galaxy, and then you see the disk with spiral arms. So these are usually spiral galaxies for which these observations are done. And what you expect is, oh God, what is that? Okay. So what you expect is that far away from the center, you have a fall off with a root of r. This is what you expect from Newtonian theory. Yeah, if the total mass was concentrated in the center, then you would just have this fall off with a root of r. Think of just equating potential energy and kinetic energy for a particle on a circular orbit, and then you get this dependence. And that's what you expect for large distances. Near the center, of course, the idea that all the mass is concentrated in the center is not so good. Yeah? But far away from the center, it should actually be a fairly good approximation. But what you observe is this here. So the curve does not go down. You do not see any fall off. It stays more or less flat over a very large distance. Yes, so even at distances where you have almost no visible matter anymore, you still have this flat rotation curve. The explanation is, the standard explanation is, there's a dark matter halo. So in addition to the mass which we actually see, there is around the galaxy, there's a kind of dark matter, we don't know what it is, but it makes itself felt by way of these rotation curves. And here this plot shows what kind of halo you need in order to explain the observations. Yeah? So these two things together, the disk and the halo, the hypothetical halo together, they can explain that the rotation curve stays flat. So, and I've also given you some profiles which are frequently used for the density in this halo. So the most important one is the Navarro-Frank-White profile, which is written here. And there are many, many of such rotation curves. This has been done for a very large sample of galaxies, and the general feature is more or less every time the same. So this was the first thing which I wanted to illustrate with a picture. Then we were talking about microlensing. Here's the general idea of microlensing. If you have a compact object at a certain distance, compact means it has relatively large mass in comparison to the radius. It's important that it must be compact. If it's not compact, if it has a big radius, then it would eclipse things which pass behind it. Yeah? But if it is compact, then it will focus the light from things behind it towards us. And then what you see is that the light curve goes up, the thing becomes bright, a star behind the lens becomes bright and then dark again. And of course, the effect is the stronger, the closer the star moves to the view line. So if it moves past the lens at a large distance from the view line, then you see almost no effect, so the light curve stays flat. But if it comes very close to the view line, then you have this very characteristic microlensing curve. And these events have been observed by the thousands, really. And I show you one example now. This was an observation from the Ogle collaboration. So you see, it was a comparatively slow event. Usually they are, the majority of them are actually faster. So you have from here to here, you have 100 days. That's an unusually long microlensing event. Usually they last only for a few days, or maybe a week or 2 weeks or so. But this is unusual. But apart from this, it's a very characteristic shape of the curve. It stays constant, then it comes close to the lens, then it goes up and then becomes constant again. And with the help of these observations, we can estimate how many compact objects are in the halo of our galaxy. So these observations are mainly done towards the halo of our galaxy. There are a few observations in neighboring galaxies, in the Magellanic Clouds and in the Andromeda Galaxy, but the majority is done in the halo of our galaxy. And the upshot of these observations was that in order to explain the dark matter which we see in the rotation curves, there are not enough machos. Yeah, machos, massive compact halo objects. These are the things which produce these effects. So at most 20% can be explained in terms of macho. In terms of machos, this was the generally accepted outcome of these observations. So what the dark matter is remains mysterious. A part of it is, so machos would be black holes, for instance, brown dwarfs, planets. Yeah, if there's a planet, there are events of this kind, where you have then a second peak here. So you have a star which produces a lensing, and then a planet which produces also an extra maximum. So there are several events of this kind. So a couple of extrasolar planets have been found with this method. Not very many. You know, we have now hundreds of exoplanets observed. Most of them have been found with other methods, but maybe a dozen or so have been detected with the help of microlensing. Okay, and the last picture, and the most important one, which I wanted to show you, is...
May I ask a question?
Sure.
So how can a planet cause such an effect? Because the radius of a planet is much greater than its gravitational radius, and how could it cause lensing?
What do you mean by gravitational radius? The Schwarzschild radius? Yes, of course. All these things, if it's not a black hole, then all of these things have also a brown dwarf has a radius which is much bigger than the gravitational radius. No, it's not necessary that it is in the order of the gravitational radius. That's not necessary.
Okay.
Yeah. But for instance, there are any hobby astronomers in the room? Maybe some of you know Algol. Algol is a so-called, well, German word is Bedeckungsveränderliche. What's that in English? Eclipsing binary or something like that, I think. Yeah. So what we see in the sky, it's in the constellation Perseus, a fairly bright star which is easily observable with amateur means. We see that the light curve goes down regularly. Yeah. And the interpretation is that we see two stars. One is comparatively big, the other is comparatively bright. And when the brighter one is behind the bigger one, then we have this dip. Yeah? Then the combined light becomes less than from the two things when they are next to each other. And so in this case, the star is too big in order to produce a lensing effect. Here the eclipsing effect is dominating. But if this star would be by a factor of 10 more compact, or in this order of magnitude, not in the order of the gravitational radius, then already the focusing effect would play a role. You can estimate what kind of mass to radius you need. It need not be in the order of the gravitational radius. So this would mean that only black holes and maybe neutron stars would produce such an effect, but that's not the case. It's not that big. Okay, and the most important picture I wanted to show you is this. I'm afraid it's not very well visible, but anyway, you see it in the lecture notes. That's a famous bullet cluster. And the bullet cluster is, in my view, the best evidence for the existence of dark matter in galaxy clusters. Not in galaxies, in galaxy clusters. And why is it called bullet cluster? It's called bullet cluster because of this shape here. It looks like a bullet rushing into a target, right? So that's why it's called a bullet cluster. And what we see here is it's actually not one cluster, it's two clusters. And what we see here are three pictures overlaid to each other. So one is an ordinary photograph with an optical telescope, was a Hubble Space Telescope which took this picture, which shows you all these yellowish or whitish spots here, which are galaxies. Each of these spots is a galaxy, not a star, it's a galaxy. And you see, there's a kind of barycenter here and a kind of barycenter here. So there are two clusters which obviously have encountered each other and have passed through each other. And this is the first picture. It's just an ordinary optical picture. Then this red thing, these red clouds, this is an X-ray photograph taken by the X-ray satellite Chandra. And what are X-ray photographs showing? They are primarily showing hot gases. Yeah? If there are hot gases, plasma, where charged particles are involved, if they are moving rapidly, then they will emit light, predominantly in the X-ray. And so what we see with these red clouds is the hot gases. And you see, you have the impression that the two things have collided, right? The stars have gone through each other, more or less without affecting each other, because collisions of stars are fairly rare. Yeah? Stars are not that big, the space between them is much bigger, so the chance that two collide is fairly small. So most of them will just pass through each other. But the gas has a certain kind of friction. It fills the whole space, and it has a kind of friction. So if the two clouds of gas collide, they will decelerate each other. And that's what we see in the picture. Yeah? The red clouds stay behind. The stars have gone through each other, but the red clouds have decelerated each other and stay behind. So far, everything fine, can be easily explained. But now the crucial thing is the blue clouds. The blue clouds is not a picture. It's actually the result of a calculation. It's a calculation of weak lensing observations. I explained last time briefly what this means. You observe background galaxies. You see them deformed because of the lensing of intervening masses. And with sophisticated statistical methods, you can get from the deformation of the background galaxies the surface mass density, which does the lensing. Yeah? So what you get, it's not the mass density in the sense of mass per volume, really distributed in the 3 space. It's only the projection on the plane perpendicular to the view line. So it's a surface mass density. And this surface mass density, this surface mass density is shown in this blue cloud. The result of the calculation is shown in this blue cloud. Now we know that in galaxy clusters, the majority of the mass is in the gases. So we would expect the blue cloud to coincide with the red clouds. But you see that by no means this is the case. Yeah? The blue clouds, which show the majority of the gravitating mass, every gravitating mass, dark or luminous, affects the background galaxies by way of lensing. Lensing is done by any mass, dark or luminous. And the majority of it, you see, has obviously also passed through each other without affecting each other. It's not decelerated by the collision. So it cannot be the hot gases, it must be something else. And it is a dark matter. Yeah? So it's the most striking observation which demonstrates the existence of dark matter if you accept Einstein's general relativity. Yeah? Of course, when you calculate the lensing, you assume that GR is correct. Yeah? If you say maybe we should modify the gravitational theory, then that's another possibility. But if you accept GR, then I think this is striking evidence for the existence of dark matter. By the way, this is, you probably cannot read it, but here it says the address from where this picture is downloaded is APOD, NASAGOV. APOD is Astronomy Picture of the Day. I don't know if you know this. So this is a website where you can find, usually quite beautiful and usually also quite interesting astronomical pictures, one per day. And this was one of the most famous in this series. So as soon as it has come out, it became Astronomy Picture of the Day, and it was reproduced in many newspapers, and probably you have seen it before. And as I said, in my view, it's the most striking evidence for dark matter. Okay, so these were the pictures when I wanted to show you. Apologies for the bad quality, but it was the best what I could achieve in this room here. Okay, and now we continue as the usual way on the board. Maybe I should open at least some of the windows. Get a bit more light. Forget it. Okay. Okay, so what I've shown you now and what I tried to explain last time was that we have evidence from quite different directions that dark matter exists. And now the question is, what is it? What is it? So candidates for dark matter. I said already, a certain portion will be just ordinary matter, brown dwarfs or things like that, but not all of it. This cannot explain everything of it. So people have suggested that there might be a kind of particles in the universe which has not been detected until now. And well, because it hasn't been detected until now, and because these clouds in the bullet cluster pass through each other, they must be very weakly interacting. Yeah? If you have something which is strongly interacting, then of course it can easily detect it, and also it would show a kind of friction effect when it passes through each other. So it must be weakly interacting. Then, at least there's no evidence to assume that the model of a dust is not a good model for this kind of dark matter. So the first thing you would try is to explain it with the help of a dust, and this works pretty well. But this means that the particles must be massive. Yeah? If they are not massive, then they would have a different equation of state. They would have the equation of state for radiation, which is pressure is 1/3 times energy density, not pressure is 0. So we need things which are weakly interacting and which are massive. And there is a funny abbreviation for this. So we call this weakly interacting massive particles. And in English, this can be abbreviated with the word WIMP, which of course also has a meaning of something which is weak. Yeah? WIMP is kind of weakling, yeah. So this typical playing with words, which some physicists like. So you have a name for them, but now you can start thinking about what kind of particles this might be, in what kind of theories they show up, and there is an enormous variety of suggestions what these kind of particles could be. And there's also a search for these particles going on, not in the sky, or not only in the sky, but also in the lab. Yeah? People search in the lab for candidates for dark matter. Unfortunately, until now, no really good, no really convincing candidate has been found. Maybe one candidate you have heard about, it's also a playing with words, it's called the axion. It's also a hypothetical particle, which is considered to be a candidate for dark matter by many. The name was introduced by Frank Wilczek, and as I said, it's also playing with words. So there's axi, of course, in this. So a kind of axial symmetry is alluded to. But on the other hand, axion is also the brand name of a detergent in the United States. So something like Meister Proper in Germany. Yeah. So it's a cleaner which you use in the kitchen. And Wilczek used this name deliberately because he thought, or he advertised the idea that if this particle exists, then it would clean up a lot of problems in theoretical physics. That's why he chose this name, axion, for it. But as I said, it's a purely hypothetical particle. Yeah, it has not been found. And there's also the idea that it might be a new type of neutrinos. We know since a couple of years that neutrinos actually are massive. Yeah? In the beginning, for many years, people thought that they had rest mass equals 0. We know by now that they do have a rest mass. And we know that there are several types of neutrinos which can change into each other. These are the famous neutrino oscillations. But if you try to explain the dark matter with the neutrinos we already know, then it doesn't work. There are not enough of them. Yeah? So we know pretty well now in which way the known neutrinos are interacting. And that's not enough. So the standard neutrinos which we know about could make up only less than 1% of the dark matter. But people have speculated that there may be other neutrinos we don't know about yet, and which are not covered by the standard model of particle physics, and that they could be candidates for dark matter. These are the so-called sterile neutrinos. Yeah? if you have heard this this catchword. But again, they are completely hypothetical.
Is it the same as right-handed neutrinos? So it's
No.
okay. So even right-handed neutrinos do not compensate this?
No. Yeah, I think these are the most important catchwords. It's not more than catchwords, which are discussed in connection with dark matter. So dark matter is a completely open problem. We see evidence for the fact that it exists, but we have not the slightest idea what it is. That's the present status. There are suggestions, but no confirmed ideas. And this has brought a couple of people to the idea that maybe one should look into a different direction. If these damned particles cannot be found, if this damned kind of matter cannot be found, maybe it doesn't exist. Maybe we made a mistake in the theory. Maybe we have to modify the theory. Instead of searching for dark matter, we modify gravitational theory. And there are a couple of suggestions. I mentioned the three most important ones. So alternative to dark matter is change or modify, let me put it this way, modify gravitational theory. And what we have to modify is actually already the Newtonian theory, the Newtonian approximation, because the rotation curves, they are totally in the realm of Newtonian physics. Yeah? If you use general relativity in order for calculating a star orbiting in a galaxy at a certain distance, or if you use Newtonian theory, that makes no difference. Yeah? So you are so far away from the center that the Newtonian theory is perfectly all right. So if you want to explain the rotation curves by modifying the gravitational theory, you have to modify the Newtonian theory. And actually, the first theory, which has been suggested in this direction, was called modified Newtonian dynamics for this reason, yeah, because it modified Newtonian dynamics. And again, this gives a nice abbreviation. It is Mond. Of course, it has absolutely nothing to do with the German word Mond. Yeah? It's just this abbreviation. And it was suggested by an Israeli astrophysicist by the name of Mordechai Milgrom in 1983. And what did he suggest? Well, he suggested to modify the Newtonian equation of motion, which is one of the best established laws in physics which we have since several centuries. But he suggested, well, what's the ordinary Newtonian equation of motion? Ordinary school physics, yeah? It is, the force is mass times acceleration. That's the standard, yeah? Okay, we need light. Or maybe, maybe we can open some of these here. Oops. And maybe also open the door. No. Oops.
I think it's enough.
Yeah? It's okay now? It's okay now? Okay, good. Okay, so that's the ordinary Newtonian equation of motion for a particle with mass m, acceleration a, force f. And what Milgrom suggested was that we modify this with a function mu, which depends on the acceleration in relation to a new constant of nature, which has a dimension of an acceleration. A naught is a constant of nature, a hypothetical constant of nature, obviously with a dimension of an acceleration, because this thing should be dimensionless. And the order of magnitude, which was necessary in order to explain the rotation curve of galaxies, was that this is approximately 10 to the minus 10 meter to second squared. So it's fairly small in comparison to our everyday units. So this would mean, as long as the acceleration is big in comparison to the A naught, then, and this is the case in experiments which we do here in the lab, then we would have to assume that the Newtonian law, the standard Newtonian law holds, So this would have to be more or less equal to 1. So if A is big in comparison to this new constant of nature, then you would have mu of the argument x. So x is the argument of the function mu, should be approximately 1, right? So then you would reproduce the Newtonian theory. But if the acceleration becomes small, if it comes in the order of this A naught, then we could modify the law. And that's what you would have to do in order to explain the rotation curves, right? If you are close to the center, then the acceleration is fairly big, and then everything is fine. Yeah, the observation can be explained with the visible matter. But if you are far away, where the acceleration is small, then we have to modify the law. So that's the reason why he modified the equation of motion for small accelerations. And where the shape of the function mu, the way in which it is specifically chosen, there are a number of choices. So for instance, one idea is one could use this here, 1 plus x to minus 1. So this would have the desired property, right? Because it's in the denominator, if the x is very big, then we would reproduce the 1. Or you could do it with a square here, then you would have to put minus 1/2 here. So that would be an alternative. So you can play around with these functions, and actually you can surprisingly well explain the rotation curves with such an ansatz. And the question is, of course, it's not very difficult if you want to explain just one particular observation to make a theory which is able to do this. Yeah, that's not difficult. The difficult thing is that you do not destroy all the other results which have been very well established by the older theories. And actually, Mond has a couple of problems. It's already fairly difficult to reconcile Mond with the observation of the binary pulsars. Yeah, the binary pulsars are by now the best test bed we have for general relativity. And with the help of Mond or its modified general relativistic version, I come to this in a minute, you have to strain the matter already considerably in order to explain this. Mond has also, or the relativistic version, has problems with observation of the cosmic background radiation. So it has already a couple of problems on different levels. It had a couple of problems before the bullet cluster was observed. But the bullet cluster then was really the greatest challenge for Mond at all. And Mordechai Milgrom himself admitted that he couldn't explain the observation of the bullet cluster within his theory. So he said, I can explain 50% of the dark matter with the theory, but the other 50% are still open. And well, if you can just explain 50% with a new theory, and the rest is still open, then in my view, it's not really very convincing to follow this up. But there's still, there are a couple of people, it's not a big community, but a couple of people who are following up on this idea of Mond. And so I think it's fair to say among the alternative theories, Mond is the one which is taken most seriously. As I said, it's a modification of Newtonian dynamics, and from a fundamental point of view, of course, the most important criticism you could put forward against Mond is that it is not a fully relativistic theory, right? It's actually, it could, at the very best, it could claim to be a theory which can act at the Newtonian level, at the level of Newtonian approximations. But it's not the real theory which is behind this. And of course, if it wanted to be taken seriously, one would have to find a relativistic theory behind this. This means a relativistic theory which gives Mond in the non-relativistic approximation. And this was hard work to do this. So this was 1983 when Milgrom did this. And the relativistic version was found in 2004, more than 20 years after that. And the person who found it was one of the most famous relativists of our time. The theory goes under the name of TeVis. TeVis is an abbreviation for tensor vector scalar theory. Tensor vector scalar theory. And the person who established this was Jakob Bekenstein in 2004. And I think many of you have heard the name Bekenstein. He is most famous as the inventor of the so-called black hole thermodynamics. Yeah? There's a formal analogy between the theory of black holes and thermodynamics. You can formulate a first law and a second law of black hole dynamics in analogy to thermodynamics. So you can associate a kind of entropy with a black hole, a kind of temperature with a black hole, and so on. And the person who invented this analogy was Jakob Bekenstein, at that time a PhD student of John Wheeler in Princeton. And Bekenstein established this theory, this Tevis theory, in the year 2004. Unfortunately, he passed away last year. He was one of the great relativists of our time. And, well, already the name suggests that it must be a fairly complicated theory, right? Our ordinary general relativity is just a tensor theory. Gravitational field is described by the second-rank tensor G mu nu. That's all. That's the gravitational field. In order to construct a theory which gives these funny laws in the Newtonian limit, Bekenstein had to assume that the gravitational field is not just a tensor field. And the tensor field also has different properties than our ordinary metrics. There's in addition a vector field, and there are also scalar fields involved. So it's a very complicated theory. And the set of equations which have to be satisfied are way more complicated than Einstein's field equation. And Einstein's field equation is already not, let's say, extremely simple, yeah? But this is much, much more complicated. So the theory, well, yeah, in quotation marks, the theory really looks awful. Yeah? So it's, and occasionally I used to say, if this theory is really realized in nature, then I don't want to be a physicist any longer. So, I really don't like the theory at all. And it destroys the geometric character of general relativity. This idea that we only have the metric which gives all the gravitational effects in terms of curvature and things like that. All this is thrown out of the window. That's not a criticism to Bekenstein. Yeah? Please don't get me right. This was great intellectual work, what he was doing. He was just trying to find out, is it possible to set up such a theory? And the answer was yes, he could do this. This was great intellectual work, but I really don't believe that it is realized in nature. So, and as I said, it really has problems with observations, with the cosmic background radiation and with other things. Also, dark matter has some problems. We talked about this briefly last time, yeah? So if you just postulate the existence of dark matter, it's not true that then everything can be nicely explained. So for instance, there are numerical simulations of structure formations with the help of these dark matter models, and they produced a lot of dwarf galaxies which we actually don't observe. Yeah? So also the standard dark matter interpretation has some problems. But I think it's really fair to say that the problems with Mond and Tevis are much, much bigger. Yeah? So dark matter is, okay, we have to modify the theory maybe in a certain way. Maybe our idea of the way in which dark matter is interacting with itself is not correct. We can modify this a little bit, but the problems here are of quite a different nature. Okay, these are these two theories which are closely related to each other. And then there's, so let me write here. So this is a relativistic version of Mond. And another one, I want to mention only one other theory. There are several actually. This goes under the name conformal gravity. It was brought forward by Philipp Mannheim. Oh yeah, around 1990, approximately. And well, this is more conservative than this here. So we still only have a metric. We don't have all these other rubbish here. We just have a metric, but the field equation looks quite different than the Einsteinian field equation. Actually, what Mannheim revived was a theory which is very old, which was suggested already in 1920 by the German mathematician or physicist Rudolf Bach. So this is the conformally invariant field equation of Rudolf Bach from 1920. And what Bach suggested was a theory where the field equation looks quite different than Einstein's field equation. Einstein's field equation involves the Ricci tensor. And the Ricci tensor, of course, is not conformally invariant. If you make a conformal transformation, if you multiply the metric with a factor, we get a completely different Ricci tensor. But there's another curvature quantity which is called the conformal curvature tensor, or the Weil tensor. This is conformally invariant. And Bach built a field equation out of the conformal curvature tensor. So the whole theory is now conformally invariant. It doesn't change if I multiply the metric with a factor. That's a problem, because you cannot have massive fields in such a theory, because masses break conformal invariance. So you have to introduce some kind of mechanism which breaks the conformal invariance. And I'm not sure if Mannheim has ever succeeded in doing this in a convincing way. Anyway, we were considering spherically symmetric solutions of the theory, which actually had been found by Bach already, which he didn't quote in this paper, in his papers, which I find rather scandalous. But anyway, so he found, or he discussed spherically symmetric solutions, which, because the field equation is different, is no longer the Schwarzschild solution. It's a modified Schwarzschild solution. And he had an additional parameter, and if we adapted this parameter appropriately, then he could explain the rotation curves of the galaxies. So that was his idea. But as I said, the theory has, in my eyes, the big problem that the mechanism in which breaks the conformal invariance, that this is not yet understood, and actually doesn't. I cannot see how it works. Okay, so these, and there are a couple of other theories, but I don't want to mention any more. But I think it's important to keep in mind that when we say that we have convincing evidence for the existence of dark matter, this is meant under the understanding that we do not want to modify the gravitational theory. Yeah? If we are willing to modify the gravitational theory, then it looks differently. And this should be taken seriously. So I don't want to sweep these alternatives under the rug. Okay, so this was the section on dark matter, evidence for the existence of dark matter. What's the upshot? If we stick with general relativity, then we are forced to assume that the majority of matter in the universe is dark. I already told you in galaxies we believe that it's something like 85%. Yeah, 85% of the matter in galaxies is dark. Only the rest is in the form of luminous matter. And in galaxy clusters, it's even a higher percentage. It's even something like 95%. That's the present status. And luminous and dark matter can be approximated according to our experience fairly well as a dust. Yeah, so in a sense, it can be modeled as a kind of non-relativistic matter. Yeah, not highly relativistic, like coming close to a radiation. So what we should take with us from this section is when we set up a cosmological model, we need a matter component, and the majority of this matter component is actually dark matter. Okay, so what I've told in this section had nothing to do with dark energy. It was about dark matter. Dark matter is a thing which is clumped in galaxies and in galaxy clusters. And now I come to dark energy. Dark energy, this is related to the distance redshift relation. So the observations which brought us towards the idea that there is dark energy is the distance redshift relation, or the Hubble law, if you want to call it this way. So I will now give a status report on observations of the distance redshift relation. I've mentioned several aspects already earlier, but now on the basis of what we have learned in the long mathematical chapter on Robertson-Walker universes and Friedmann solutions, we can now discuss this on a more solid basis. I think I have to remind you of some results from this long chapter, because I will need these results now. So the first thing is, well, actually, when we talked about the Hubble law, we had the Hubble law in several different versions. So one version was that we could write the Hubble law as an exact law, that's no approximation, in an arbitrary Robertson-Walker universe in terms of the proper distance. That we say the time derivative of the proper distance, this is the ordinary t coordinate in a Robertson-Walker universe, is a Hubble constant we observe at a time to times dp. And what was dp? dp was the proper distance. So the proper distance was, if I observe here, so this is time here, this is the time, and this is a radius coordinate. We could use the coordinate chi or the eta or whatever you like. The proper distance is the distance measured in this section here. So if I have here a distant galaxy, that's our position, then this distance here, measured with a metric, that's the dp, at the time where the observation is done, at the time to. It's an exact law. It holds in any Robertson-Walker universe, but it is not related to any kind of observations. Yeah, I've emphasized this already, because this is something we cannot measure. What we can measure is only what arrives towards us, arrives at our position via a light ray. And light has to start much earlier, not at the same time when it arrives. So this distance is something we cannot measure. So it's a nice mathematical law, but it's not related to observations. So when we are saying we link the Hubble law to observations, we do not mean this law, not related to observations. So here in this law, the Hubble constant really appears as a factor between a distance and a velocity. Yeah? This has obviously the dimension of a velocity. This is the distance divided by t gives the velocity. So this also explains the dimension for the Hubble constant, right? It has a dimension 1 over time. And if you express this in kilometer per second and this in megaparsec, then you write this dimension 1 over time in the funny way, kilometer per second divided by megaparsec. That's the usual way in which the Hubble constant is given. Okay, but that's not the law which we relate to observation. What we relate to observation is the Hubble law as a relation between distance and redshift, because redshift is observable. So as a relation between redshift. Yeah, and then we have a couple of alternative possibilities. When we say distance, there is not a unique distance in the cosmological model. And the one which is related to observations in the strongest way is a luminosity distance. So we usually choose this. And we derived this relation. So the luminosity distance was denoted dl. And then we have, where's the c? Here, c z divided by hto. That's a linear law. Yeah. So the redshift is related in lowest order, of course, to the luminosity distance by a linear law. And up to this order, it doesn't matter which kind of distance we are choosing, because all of them coincide up to this order. But if you want to go beyond this, then we get something else. This is 1 minus q of t naught. What was the factor? cz squared over 2 h of to squared. No, h of to. Okay. And the higher order terms. It's linear in z, quadratic in z, then comes the cubic term, and so on. So if we are satisfied with the second order, we have 2 parameters in the game, the Hubble constant and the deceleration parameter. Okay, and that's what can be tested, because the redshift can be observed directly, and the luminosity distance, well, this can be measured if we have standard candles. Yeah, the luminosity distance is related to the flux, just to remind you. The flux was L over 4 pi dl squared, where L is really the intrinsic luminosity. Yeah, really a measure for the energy which is emitted by the source. And the dl squared is defined in such a way that this equation holds. So that the flux which arrives here is just given by the luminosity divided, the true volumetric luminosity divided by 4 pi dl squared. So if I know the L, then the dl gives me the flux which arrives here. That means it gives me the brightness in the sky. And astronomers usually don't use the f, they use the magnitude, which they denote the apparent magnitude, which they denote little m, and it's related by a logarithmic scale to the L. So this is minus 2.5 log to the base of 10 of L, plus 2.5 log to the base of 10 dl squared, plus a certain constant m naught. So if I know the intrinsic luminosity of the source, this is a constant. It's just introduced in order to fit this scale to the old historic scale, which was introduced by the old Greeks. Yeah, this scale where the stars have magnitudes from 1 to 6. Yeah, and in order to bring this as close as possible to this old scale, one has chosen these factors and this constant m naught. So the relevant thing is that you have a term which is given by the L. So if you have standard candles, this is known. And then comes the dependence on the dl. So there's a unique relation between the magnitude and the dl squared. So if I have standard candles, and if I observe the apparent magnitude in the sky, this gives me the dl. In this way, the dl is measurable. And the z is measurable directly. So this is what we want to test with the help of observations. So we need standard candles. I come to the possible candidates for standard candles in a moment. And well, this holds in an arbitrary Robertson-Walker universe. So you don't need any assumption, and you don't make any assumptions about the matter content. Yeah, it is just this holds in any Robertson-Walker universe, and you have this dependence on these two parameters, h of TO and q of TO. If you do make an assumption on the matter content, then you can give can make stronger statements. And we have done this in great details for a dust universe. For a dust universe without a cosmological constant. Yeah, pure dust, nothing else, just the cosmological, just dust. Remember the solutions, we have discussed this in great detail. There are the three cases. This is k equal 1, this is k equal 0, and this is k equal minus 1. So k equal 0 is the Einstein-de Sitter universe, which for many years was the favorite cosmological model. And for these models, for all three cases of k, we have a closed form equation for the distance redshift relation. This was the Mattich formula. So we can write them exactly, not just up to a certain order, not just the Taylor expansion, which has been broken off here, but exact, up to arbitrary order. We have this equation, dl is, what was it, c h of TO. And it's an equation in terms of the h of TO and the q of TO. These two parameters are sufficient for these models in order to give the exact equation. Q of TO z plus Q of TO minus 1 square root 2Q of TO z plus 1 minus 1 bracket and another bracket. Okay, that's it. This is a little bit too low. That's what I mean. So for a dust universe with lambda, and actually when we now discuss the observations, that's what we would need, there's not such a nice formula. Oh, I forgot to mention, if you don't want to use a Q, instead of the Q, you could also use the omega m. Yeah, we have a dust universe, so there's only one density parameter. It's the density of matter, which one usually denotes capital omega with index m. And this is uniquely related to the Q by a very simple formula. We have done this on one of the worksheets. So you can replace the Q of TO by the omega m if you like to do this. So if you match this formula, if you try to match it to observation, and if it works, then it tells you not only the value of the h and of the q, but also the value of the omega m. So If you do this for a dust universe, then that's a very nice and very, very concise situation. It's not so nice for dust with cosmological constant. For dust with lambda, actually I told you that you can write down the solution in analogy to this here, to the cycloid and so on. You can write this down, but it involves elliptic integrals. And I didn't do this on the board in detail, I just discussed it qualitatively. So there is a formula, I haven't given it and I will not give it, formula for the L as a function of that. It will not have this simple form. It will be much more complicated. It can be given in terms of hyperelliptic functions. No, elliptic functions. Elliptic. But it looks pretty awful. So I didn't do this, and I won't do this here on the board. But there is something like a matic formula with lambda. Of course, now it involves one additional parameter, namely the omega lambda. Yeah? Now we have not only the omega m, we also have the omega lambda. So now it involves also omega lambda. So these are the things I wanted to remind you of. And now we can discuss what the observations are actually showing. So you can, when you observe the luminosity distance or the magnitudes of some standard candles and relate it to Z, we could either use this formula. Then it would give us the H and the Q. Or we could use one of these formulas. Then you would have to specify the matter content. So maybe you would begin with the simplest idea that we are just living in a dust universe. You would use this formula. And then you would try to fit it to this formula. If it doesn't work, you make it more complicated. You try to fit it to the formula with a lambda. And that's exactly what has been done over the last several decades. And I will now briefly run through these kind of observations. Is there a question? Or? No.
Is it possible to open the window?
I try. I'm not sure if I'm able to do this. This works, yeah. Okay. Is that better? Okay. Okay, so, well, the story began. No, actually it didn't begin with Hubble, but the first, really important and the breakthrough of this line of thought is related to the name of Edwin Hubble. This was in 1929. And, well, he was the first who claimed that there's observational evidence for such a linear relation between the luminosity distance and the redshift. And he used data. If you look at where we are in the year 1929, you have to remind yourself the nature of what they called nebulae at this kind, what we now call galaxies. Yeah? This had just been clarified a short time before this. In the year 1920, there was a famous Shapley-Curtis debate. Have you heard about this? So these were two of the most famous American astronomers, Heber Curtis and Harlow Shapley, and in some university in the United States. So they had a debate about the nature of these of these nebulae, as I call them. And Shapley said they are within our own galaxy. Yeah, maybe at the boundary of our own galaxy, but not far away from our own galaxy. And the whole world is our galaxy, with a little bit around it. That was in 1920. Yeah? This was the idea which one of the most famous astronomers of this time was still advocating. And Curtis said, no, they are galaxies. They are galaxies like our own galaxies, and they are far away. Yeah? The idea, of course, was around. Kant, the German philosopher, had already the idea that these fuzzy spots in the skies are similar to our own Milky Way. But it was by way not, it was absolutely not established. And it was actually Hubble who gave strong evidence in favor of Curtis when he observed variable stars in the Andromeda galaxies. Variable stars of the type which are called Cepheids. Yeah? So these were the standard candles which were used at this time. What are Cepheids? Cepheids are variable stars. Actually, we believe that they are pulsating stars. That's what makes them variable. So so the light curve goes up, down, up, down, up, down, fairly regularly. And it was observed with Cepheids which are close to us that there's a universal relation between the true luminosity of these things and the period. Yeah? And this was then extrapolated to Cepheids which are farther away. Some of them could be observed, for instance, in the Andromeda galaxy, as I said. And then they could be used as standard candles. So with the help of this relation between the period and the true luminosity, you can find out how far away these things are. And that's how Hubble determined the distance to the Andromeda galaxy. And this made clear that it is a galaxy by itself. Yeah? It's not something very close to us, but it is a Milky Way by itself. So this was just in the 1920s. And then Hubble carried on. So he tried to find out how the distance and the redshift of galaxies are related to each other. There was already a certain catalog of redshifts of galaxies. It's not too difficult to measure the redshift. If you can identify spectral lines, and that's pretty straightforward. But it's very difficult to measure the distance. Yeah? If you have Cepheids, of course, then you can use this as standard candles. But Cepheids have been observed only in very few and only in the closest galaxies. So what Hubble did was that he just estimated the distance of galaxies by their total brightness. Yeah? So extend this. So this works only for galaxies which are very close to us, so that we can identify Cepheids inside of them. So then extend this to galaxies farther away. By estimating the total luminosity. And that was actually the way in which Hubble, in his famous 1929 paper, came to the values for the luminosity distance. It was, for the majority of the galaxies, it was just an estimate of the total luminosity, so it was fairly rough. And you will not be surprised to hear that because of this rough estimate, the data were not very clean. Actually, they were scattered over this. If you plot the diagram, that's what we call a Hubble diagram. He was the first who did this. So he plotted over the redshift the luminosity distance. And there's a big scatter. Well, if you look at the diagram, you see clearly that there's a tendency that the whole thing goes up. But that it is really a linear law, that is really a straight line. It's very, you need some kind of imagination in order to read this from the data. And were only very few data. I think it was 25 or so. Yeah, so he just in this order of magnitude. So, but nonetheless, he claimed boldly this establishes the fact that there's a linear relation between distance and redshift, what we now call the Hubble law. And actually, he estimated the parameter, which we now call, of course, he didn't call it the Hubble law, it's the Hubble constant, obviously. He called it the K factor, capital K. That was his notation. So what we now call, nowadays we denote it this way, h of t naught or just h naught. And he came to the conclusion that this would be something like 500 kilometer per second per megaparsec. You see, this is far too big, actually. If you compare this to the value in which we believe nowadays, then this is it's almost a factor 10, factor 9 or so. And what's the reason for this? Well, first of all, that the fact that the data, and actually I should also say, the Z was not very big for his data. So actually he observed galaxies which in cosmological dimensions are very close to us actually. So I think the biggest Z he had was something like 0.01 or something like that, in this order of magnitude. So they were fairly close. And if they are fairly close, then the proper motion of the galaxies plays an essential role. Yeah? So we have on very large scales, we have this Robertson-Walker symmetry, homogeneous and isotropic, and the galaxies move on these integral curves of the standard observers. But if you look at smaller scales, then of course the galaxies have a certain proper motion. So our own galaxy is a member of the local group, and the members of the local group, each individual member doesn't follow one of these integral curves of the standard observers. They are gravitationally bound, they are moving around each other. Then there's a Virgo cluster close to us which pulls us towards itself. So this also has a strong effect. So if you look at this at small scales, you have these proper motions, these individual motions overlaid. And that's the second important reason why this was not more than a fairly rough estimate. And, well, the main reason why this factor is too big is that the distance ladder at this time was wrongly calibrated. So the Cepheids, with which everything starts, the Cepheids were not properly calibrated. Yeah? So all the distance measures were off by a considerable factor at this time. So this was found after a while. So in the 1950s, people realized that one has to recalibrate the distance ladder, and this means that the Hubble constant became smaller at that time by a factor 2.5 or so, and at the same time, of course, all the distances became bigger. Yeah? If the Hubble constant becomes smaller, then the distances become bigger. This means all galaxies were actually farther away from us than one had thought until this time. So there was a recalibration of distance ladder. And of course, the observations had been carried out to bigger values of that to a certain extent. So the linear law had now come out fairly cleanly. But there was still a certain scatter and a certain debate about the true numerical value of the H, and there was at this time no way of determining the deceleration parameter. So it was just about the linear law. Deviations from the linear law were beyond everything what was observable. So and then it was since the 1990s, and not since until I mean. We then believed that the Hubble constant had a value, well, between 50 and 100 kilometer per second per megaparsec. And actually there was, similarly to the Shapley-Curtis debate in the 1920s, there was also the debate in the 80s or so, between people who advocated a value close to 50 and a value close to 100, and this was open over several decades, and the Q actually, as I said already, there were no really reliable data, so you couldn't really see something like a curvature in the graph of the distance redshift relation. But there was a tendency to assume that it probably lies close to 1/2. This was mainly motivated by the theory, because the theorists advocated the Einstein de Sitter universe, and the Einstein de Sitter universe has a Q of T O 1/2, right? So omega m, if I have a pure dust universe, then omega m equal 1 means k equals 0. Yeah? 1 is a critical value. That's the sum of all omegas is equal to 1. This means that we have k equals 0. And here we have only one omega, so omega m equal 1 means k equals 0. This means Einstein de Sitter. This means q equal 1/2. So if you look in, I don't know, Weinberg's book or something like that, cosmology books which were written before 1990, around 1970 or 1980 or so, So you often find the sentence that, yeah, there's some good reason to assume that we live in a universe with q equal 1/2, which means decelerating, right? Q is a deceleration parameter. And then came the revolution, really the revolution, in the year 1998, 99, when a new kind of standard candles had been used in order to drive this farther to bigger values of Z. And this new kind of standard candles were the supernovae of type 1a. So let me see, where do I write this? So the papers from the two collaborations were published in 1989 and 1999, 98 and 99. And well, there were two collaborations. One was called the high redshift supernova search. And the other one was called, let me see, Supernova Cosmology Project. I think that's it. Yes, exactly, Supernova Cosmology Project. So these were two collaborations which worked independent of each other, but they did the same thing, Supernova Cosmology Project, and they came to exactly the same result. So there are two possibilities, right? The first possibility is they found the correct result, so nature is really the way as they predicted, or they both made the same mistake. Yeah? So they could of course also be. So they made similar assumptions, and if both of them made the same kind of wrong assumptions, then of course they would also reach the same result. But whenever you have the result from two independent groups, of course, that's always a stronger result than it would just have been done by one group. And yeah, so they used a new kind of standard candles, the supernovae of type 1a. So what's the problem? The problem is that it's not so easy to find standard candles at large distances. Yeah? So we need light sources about which we know what their intrinsic luminosity, and they must be available at large distances, because otherwise we cannot use them for cosmology. And before this project, we didn't have standard candles of this kind. And these supernovae of type A were really the first standard candles which were able to fit this gap. So they are supernovae, so they are very bright. So they can really be seen in distant galaxies. Actually, when we say high redshift, maybe I should clarify what this is. You know what's the highest redshift of a galaxy which has been observed by now? 6, 7? That was a few years ago. This year in March, there was a galaxy with Z equal 11. Yeah, 11. It's called GNZ11 yeah, so for this reason. So that's a record holder right now. So you might think when we're talking about high redshift supernova that it's in this range, yeah, maybe 7, 8, 9, 10, something like that. No. So this were at this time all these supernovae were still below Z equal 1, yeah, but they were at high redshift in comparison to the standard candles which had been used earlier, yeah. So I think the highest redshift in this sample was Z equal 0.8 or something like that, 0.83 maybe. And but in comparison to what has been used for the distance redshift relation before, this already was a very high redshift. Yeah? So high redshift means still Z smaller than 1. And yeah, why are these, well, what are these supernovae? Maybe I should say a few words about this. So supernovae, the idea of a supernova was introduced in the 1930s by Bade and Zwicky. And Bade then also made, together with Minkowski, a classification of supernovae. By the way, that's Rudolf Minkowski, yeah? Not to be confused with Hermann Minkowski. He was the uncle, actually. Hermann Minkowski was his uncle. Hermann was a mathematician. He was Einstein's teacher in Zurich. And Rudolf Minkowski was a German-born astronomer who then lived in the United States. And he was one of the pioneers of supernovae. So the classification of supernovae, by Bade and Minkowski was very simple. At that time, this was in the 1930s, there was type 1 and type 2, period. Type 1, type 2, and the distinction was just made by no hydrogen in the spectrum or hydrogen in the spectrum. Yeah? And then in later years, this was a finer classification was made, and in particular, the type A were divided into AA, 1A and 1B, C. And the distinction was now that here we have a certain silicon line, absorption line. And here we have no such line. And what one found out was that a certain subclass of this 1A, not all of them, a certain subclass of them show a very distinctive relationship between the shape of the light curve, which is observable, and the true luminosity. And where the idea, how this comes about, this is not just an observation, there's also a physical explanation for this, there's a theory behind this. The idea is that this kind of supernovae, this supernovae of type 1A, that they are collapsing white dwarfs. So a white dwarf is, as you probably know, one of the final states a star can have. Probably to all we know, also our sun will end up as a white dwarf. So if a star has burned out its nuclear fuel, one possibility is that it just collapses, forming a kind of degenerate state, which is called a white dwarf, which is perfectly stable. So if it just sits there, if you don't perturb it, it will sit there forever. It's a stable final state of a star. Now it may happen that such a white dwarf exists in a binary, so that it has a companion, and that the two things orbit around each other. And then, if they are sufficiently close to each other, matter from the other partner will be accreted by the white dwarf. What's the effect of this has is, of course, that the mass of the white dwarf becomes bigger. And there's a limit for the mass of a white dwarf, which was found by Chandrasekhar, which won him the Nobel Prize, which is 1.4 solar masses. If a white dwarf is heavier than that, then it's no longer stable. Yeah? So I said, if you don't perturb it, it will sit there, it will be stable. But if you shove mass onto it, then the mass will increase and the thing will become unstable. And this will happen at a very particular mass, namely if this limit is reached. And that's the reason why all these things have more or less the same luminosity. Yeah? Because it always happens at the same, when the mass has reached a certain critical parameter. That's our understanding how these supernovae of type 1A come about. So they are white dwarfs in the binary system. There's mass accreted by the white dwarf partner, and if the mass supersedes the Chandrasekhar limit, then the thing will explode in the form of a supernova, and that's what we observe. Unfortunately, we don't know it in advance, and that makes these observations difficult, right? So you don't know in which galaxy at what time a certain supernova will explode. So if you make a proposal, write a proposal as an observer for at a big observatory, you want to observe supernovae, and then you get certain observation time, and you are unlucky. There will be no supernova. This has actually happened. The first supernova project where they searched for these supernovae of type 1A was already in the 80s. It ran over, I don't know, several months or so, and they found just one supernova, yeah, in this period. So you can have just bad luck. So this is that's how it is with these things which you cannot predict, and they are not very common. So in an ordinary galaxy, you have maybe one per millennium, something like that. Yeah. So they are not that common. So that's the reason why the number of supernovae of type A which were available for this project was not very high. And the first papers which appeared from these collaborations were, well, even a little bit ridiculous. Yeah? They reported about 2 supernovae, 3 supernovae, something like that, and they made statistics with this. Yeah? So this is a little bit, questionable. But in the end, I think they had something like 40, 45 or so. And okay, you can do statistics with this. There's a question?
Yes, until which redshift one could distinguish the supernovae from the galaxy?
Let me answer the question in a more general way. It's how to distinguish the supernova from the host galaxy. Actually, this is a problem. So what you see, when you see the light in the supernova, there's also the background light from the host galaxy, which has to be subtracted. And for this reason, when such an observation is done, also the host galaxy is carefully observed after the supernova has, or you look into old data, if maybe you have data from the time before the supernova went off, yes. Of course, you have to take this into account, yeah. And, or was it about the number, how far away this thing can be? Yeah. Yeah, okay, there are now a few at redshifts bigger than 1. But I think it's not much bigger than 1, what we have until now. And as I said, at this time, when these 2 famous papers appeared, it was just below z equal 1. So what have I written here? Classification. So your supernova of type 1a. So actually, as I said already, you have to single out some of the supernovae of type 1a because not all of them follow this clean relation between total luminosity and the shape of the light curve. So you have subclasses which are called 1an and 1ax and things like that, and they have to be taken out. But let's trust that the people who did this observation, that they did this carefully. And so then they had a certain sample of galaxies and the distances to which these equations could be applied. And what they found, well, I said already, you can apply the equations in 2 different ways. You can either use a general form without specifying the matter content. Oops. Then you would use this formula here. So you could read from the observations the H and the Q, or you could make a certain matter model. That's actually what's done in this paper, in these papers, usually already at a very early stage. Then you could try it with the dust, and if it doesn't work, and actually it didn't work, you do it with the dust with a cosmological constant. And that's what they did. So now let me report the results. So the results were, well, for H, they found something of approximately 65 kilometer per second and megaparsec. We believe now that probably the correct value is a little bit higher. So the observations from the cosmic background radiation give something closer to 70, maybe even a little bit over 70, but certainly in this order of magnitude. And the striking result was that they found clear evidence for the fact that Q of TO was negative. So the most likely value was something like -1. Not +1/2, but rather -1, but with a very high uncertainty, with a very high statistical uncertainty. So it could be closer to 0, but it was definite that it was negative. So the data were quite clear. That Q is negative was established at a confidence level, I think, of 7 sigma or something like that. Yeah, you know, sigma is a standard deviation. So you have, if you have a Gaussian distribution, then you have within 3 sigma, you have, what is it, 99.8%, I think, of all data points. Yeah? So usually you say 3 sigma, that is a certainty from a statistical point of view. And this was even, I think it was 7 sigma. So it's practically 100%. Yeah? You can practically to 100% exclude that on a statistical basis, yeah? If all the theoretical assumptions are true, that we live in a decelerating universe. We have an accelerating universe, and this means it is impossible to fit the data to this equation, yeah? Because all these models are decelerating. So the models with pure dust were out. From this moment onwards, they were out. They were the favorite models up to this moment, up to 1998, but now they were out. It's impossible to fit these. And the next thing what these people did in these two collaborations was they tried it for dust with a cosmological constant. Yeah? So now you have an omega m and an omega lambda. And the way in which it is usually plotted, I think you have seen these plots before, is, that you plot here the omega lambda, here the omega m. So you know that omega m plus omega lambda, equal to 1 means that k is equal to 0. So this is, if you have here 1 and here 1, you mean that on this line you have k equals 0. Yeah? This is k equals 0. Here you have, wait a minute, if the density is smaller, you have k equal minus 1, and here you have k equal plus 1. And well, the formula, which I haven't written down because it's so complicated with the elliptic intervals, so this formula tells you that the Q is, always keep in mind these things are actually time dependent. Yeah, this means omega lambda now, omega m now. That's what is plotted here. That the curve where this is 0, that this lies here. So here we have the accelerating models, here we have the decelerating models. And the data which they had, they gave something with a, say at a confidence level of, I don't know, 59% or so. They showed something like that. Maybe a bit closer here. Of this form. So that we are in this region. So definitely, as I said, Q is negative. So we have an accelerating universe. Yeah, here is Q is equal 0. So we are far away from this line. And well, now the question is, do we believe that we are exactly on the k equals 0 line? There are theoretical arguments from this, and they come from inflation, right? If you believe that there was inflation at an early stage of the universe, then whatever the curvature was in the beginning, after the inflationary period, the capital K is practically 0, very, very close to 0. And this means little k equal to 0 is a very, very good approximation. And then we must have this relation. We must be on this line. And if you assume this, then it would be here. It's well inside this region, which is advocated by these observations. Then we get something like omega m 0.3 and omega lambda 0.7. That's the numbers which you can find in these papers. And it's really amazing that these two collaborations, which worked independently of each other, that they found more or less exactly the same result. Yeah? So this is the reason why we believe that there is something which you might call dark energy, or you might call it a cosmological constant, or you might call it quintessence. Yeah? We have this kind of reinterpretation. It is this here. And in addition, we have the matter, and matter means dust. It's a dust model. For this consideration, yeah, the observations from the redshift distance relation, this of course doesn't tell us whether this is dark or luminous. Yeah? Matter is just matter. It's modeled as a dust, but from these other observations, yeah, from the rotation curves of galaxies, from the instability or from the apparent instability of galaxy clusters, which we want to avoid, and from the weak lensing observations, we know that this is, to the larger part, this is dark matter. Yeah? But it just jointly considered as a dust. So the main result which comes from the supernovae projects was that the dust alone doesn't do it. The assumption that we live in a universe which now can be explained only as filled with a dust, that this is a good approximation, and this assumption was wrong. We need, in addition, in approximately the same order of magnitude, right? These are not so far away from each other. Actually, you could expect that they differ by a factor 1,000 or 100,000 or something like that, with just a factor of 2 approximately. So that's also something many people are worried about. Is this a coincidence that we are just living at a time where these two contributions are very, very similar to each other? So this, in the whole development of the universe, this is true only for a fairly short period of time, right? And we are just living in this time, where the omega lambda and the omega m are almost the same, if they are very similar. Okay, but anyway, maybe it's just a coincidence. We must live at some instance of time. Why not at this instant where this relation holds? Yeah? So actually, I don't think that this is a big problem. But we need this contribution from the omega lambda. And at this time, I think in '98, the name dark energy was invented for this, right? So because we don't only need this here, the dark contribution to the matter, which is clumped in galaxy and galaxy clusters, we need at this level where we discuss the universe in the approximation that it is completely homogeneous. At this level, we also need this dark component. Yeah? And here Michael Turner suggested the name dark energy because nobody came up with a better name. So actually, it's not a very insightful terminology, but it's anyway, one has to call it one way or other. And then, of course, all the other interpretations came up that you could interpret it as a perfect fluid with a certain equation of state, that you could interpret it as a scalar field. Also, the name quintessence, I think, came up around this time. As the idea that there is a scalar field which gives a considerable contribution to the matter content of our universe was older. This was already in the 80s. I think the first was Wetterich who suggested this. Christoph Wetterich, the German cosmologist, he called it the Cosmon field. What we now call quintessence, he called it the Cosmon field. And also there was a famous paper by Ratra and Peebles from the 80s, where also a scalar field was suggested. But this really linked this to observable features and made it really necessary to introduce something of this kind. You can interpret it as a scalar field, as a perfect fluid, or whatever you like. Okay, this is, you know that this was awarded the Nobel Prize in 2011. Yeah. Nobel Prize 2011. It was for Perlmutter. He was a leading scientist of this project, and then from two leading scientists of the other project by the name of Schmidt and Ries. And this kind of observation goes on. Yeah, this goes on. So there's also planned to do it from space. There's a project, a satellite project, where this kind of observation should be done from space. So there's a planned space project. Like many projects, in particular in the United States, it has been delayed because other priorities have come up. So in the beginning, this was called SNAP, the Supernovae Acceleration Project or Proposal. Yeah. Then, but later it became part of what is called WFIRST. Don't ask me what this is standing for. And so it's now a partial project of a bigger project, which is called WFIRST. This is an infrared project. It might be launched, I don't know, around 2020 or so. I think WFIRST is, I think it has been, so it was successful in the last round when the financial funding was discussed. So I think this will fly sometime in the future. And so this will continue this observation of supernovae at cosmological distances and probably push the observations to bigger values of Z. Okay, just a quarter past, so very good. So this was what I wanted to say about the distance redshift relation. So what we should take away from this is that we now have good evidence for the fact that our present universe must have an omega lambda and an omega m. And actually the supernovae alone do not give very strong evidence for the fact that we live at k equals 0. Yeah, this comes from somewhere else. I will come to this. But at least it is consistent with the assumption that we have k equals 0. But actually, the barycenter of the observations is a little bit off this curve. So we will then, next time we will talk about the cosmic microwave radiation. And when we combine this with this observation, then you will see that we get stronger evidence that we are somewhere here. And that this idea of lambda CDM cosmology, that this comes fairly close to what we observed today. Any questions? If not, see you on Friday. On Friday, I will do a 90 minutes lecture. Yeah, because last time we lost now, and I want to get this time back. Okay, see you on Friday.